In the first part of 2.5, we are going to look at some properties of functions. Okay, so the first thing, it's just always important to remember that when we're dealing with graphs, we always look at the graphs from left to right. Right? We're always looking from left to right. So the first idea that we're going to look at is increasing and decreasing. So as we move from left to right, we say the function is increasing if the y values are going up. Right? Or if the y values are increasing. The function is decreasing if the y values are going down. And we say that the function is constant if the y values are remaining the same. Okay, so let's take a look at this example over here and describe the intervals on which the function is increasing, decreasing, and constant. Okay, so the first portion of this graph, okay, starts here and is increasing all the way up to here. Now, when we write intervals to describe where a function is increasing or decreasing, we are always talking about the x values. Okay, so I'm going to say that this function is increasing on the interval -3 to 1. Okay, I'm talking about the x values where this function is increasing. So for this example, we're going to say it's increasing on the interval -3 to 1. Okay, now we always use an open interval. Okay, we always use an open interval because we say right here at 1, the function is not increasing anymore. Right? So whenever we're talking about these intervals, we're going to use parentheses. Okay, and we're not going to include the endpoints. We say the function is decreasing then, well, from here to here. Okay, the function is going down. So we describe that by using the x values. So we're starting at 3 and going to 5. So on the interval 3 to 5. Right? And remember, these are intervals, not coordinate points. And then finally, this graph is constant right here. Okay? The y value is remaining exactly the same. So that is on the interval 1 to 3. Okay? So the next idea is maximum and minimum. Okay? So you may want to pause the video here to jot down these definitions. Okay? But I'm going to talk through them here, and then we'll look at an example. So a relative, or also known as a local max, is just a point where a function changes from increasing to decreasing. Okay, we could also call that like a hill. So just a small little example could be, a function that does this. Okay, so right here would be a local maximum value. Okay, right there would be a local max because the function is changing from increasing to decreasing. Okay, that is a local maximum value. And when we're looking at a graph, okay, what we're looking for are the little hills. Okay, that's where we'll see the local or relative maximums. Then for the relative min, similar idea. Okay, we could have a function that does this. And then this point right here, where the graph changes from decreasing to increasing, that is a relative or local min. Okay, that point right there. And when we're looking at graphs, okay, that's just like a little valley, anywhere we see a valley in a graph. A turning point then is just a local max or min, essentially. Okay, a point where the graph changes from increasing to decreasing or vice versa. Right? And then we can also talk about absolute maxes and mins. So an absolute maximum is the greatest y value that a graph or a function reaches. Okay, and now not all graphs or functions would have an absolute maximum value. If we think about this graph, this little parabola that I drew right here, it keeps going up forever in both directions. So it goes up to positive infinity, right, it's not going to have an absolute maximum value. But this one would. Okay, in this case, this relative maximum, okay, if this is just a parabola, this relative maximum would also be an absolute maximum. Okay, same idea for an absolute minimum value. An absolute minimum is the smallest y value that a graph or a function reaches. And again, not all graphs will have an absolute min. So in this first parabola that we drew, this function would not have an absolute min because it goes to negative infinity. Right? This one would have an absolute min, though. This relative minimum would actually still be an absolute min. Now, I put a little note down here as well to make sure that we remember an endpoint. Okay, if we have a graph that stops on the left or the right and doesn't continue on forever, it is possible for an endpoint to be an absolute min or a max. It could be the absolute highest or lowest y value that we reach on the graph, but we would not describe it as a relative min or a max. Okay. So an endpoint can be an absolute minimum or a maximum, but an endpoint cannot be a relative minimum or a maximum. So let's take a look at an example. Okay, so we want to find all relative and absolute mins and maxes. Okay, extrema or extremum is just another word for mins and maxes. So let's list them out here. Okay, so my relative mins. Okay, so I'm looking for any place where there is a valley. So I see right here, okay, this would be a valley. So that's the point -3, -2. Right, and then I see another one right here. So that's the point 2, 0. And I think that's it, right? Those are the only two valleys. Okay, so let's do relative maxes. Okay, so those are the points where we are changing from increasing to decreasing. So I see one right there, and right there. Looks like we have three of them. So this is the point -5, 1. This is the point 0, 3. And this is the point 4, 1. Okay, so now let's talk about absolute mins and maxes. Okay, so absolute min is the smallest value that the graph reaches. But now I see on both ends here, my function is going to go to negative infinity. That means that there is no absolute min, since my graph continues on forever down in the negative direction. We would, however, have an absolute max. Okay, the absolute max would occur here. Okay, this is the highest that the graph is going to reach, because I know that on both ends, okay, my end behaviors both go to negative infinity. So I do have an absolute max. Okay, at 0, 3. Okay, and in this case, that 0.03 is considered a relative max and also the absolute max. Okay, so this is how we would identify those types of points from a graph. All right. So let's do another one here where we're identifying intervals of increasing, decreasing, relative mins and maxes, and turning points and absolute mins and maxes. Okay, so first, the intervals where the function is increasing, right? Those are where we are going up as we look from left to right, where the y values are going up. So that's going to be here and here. Okay. So let's highlight increasing. So let's list those intervals. Okay, so remember, we're only talking about the x values when we're talking about these intervals. So that's going to go from an x value of 3 up to an x value of 6. So my first increasing interval is the interval from 3 to 6, and it is an open interval. Remember, we're always using open intervals because at these points right here, the function is neither increasing nor decreasing. Then we're going to say, we're going to union that with my next interval. So 6, 7. So we're starting at 8 and going up to 1, 2, 3. So up to 11. So my function is increasing on these intervals right here. So let's take a look at decreasing then. Okay, so as I look from left to right, my function is decreasing here, it's decreasing here, and decreasing here. Okay, so let's list those intervals. Now, since I have arrows telling me that this function is going to continue on forever in this direction and forever in this direction, we're going to have some infinities in this one. Okay, so this function is going to continue on forever this way. So I'm going to start at an x value of negative infinity and go all the way up to 3. Okay, so this function is decreasing from negative infinity to 3. Okay, now sometimes students are tempted to say that the function is increasing on this interval because we see that it is going up. However, we always need to make sure we're looking at the graph from left to right. Okay, so from left to right, this function is decreasing, or this piece of the function is decreasing. All right. Then my second interval would be from 6 to 8. And my third piece would be from 11 to infinity, because this graph is going to continue on forever in that direction. Okay, so these are my intervals of increasing and decreasing. Now, let's do relative mins and maxes. So maxes first, so that would be right here. Let me get a different color. Okay, so right here and right here for my relative maxes. So that would be the point 2, 3, 4, 5, 6, 6.66. And my other one is at 11, 12, 11, 12. Okay. It's another small thing. Okay, just make sure these notations look very similar, even though these are intervals. These are coordinate points. Okay, so just make sure you don't get those two ideas confused. So then relative mins, looks like we have 2 of those as well, here and here. So that would be the point 3, negative 2, and 8, 1. Then turning points, okay, actually all 4 of these, both my relative maxes and both my relative mins, would be considered turning points. Okay, so we would just list all of those. 3, negative 2, 6, 6, 8, 1, and 11, 12. Then finally, my absolute mins and maxes. Okay, my absolute min, it appears that it would be right here. However, this function is going to continue on forever in this direction. That means there is no absolute min for this graph. Actually, same idea for absolute max. Right? It appears that it would be here. However, this part of the graph is going to continue on forever in this direction. So that tells me there is no absolute max either. Okay? So our next idea is even and odd. This is really similar to something that we've already done because these are symmetry ideas. Okay, so an even function is just, in terms of algebra, is saying if I plug negative x into my function, I get exactly what we started with. So if you remember, okay, we talked about symmetry like this. An even function is then symmetric about the y-axis. Okay? So if I plug negative x into my function and I get exactly what I started with, the graph is symmetric about the y-axis. Now, an odd function then, we say if we plug in negative x, we get the exact opposite of what we started with. Okay? Every term in my function would have the opposite sign. And we'll look at what that means here in a second. An odd function is symmetric about the origin. Okay? So let's first look at this from a graphical perspective, and then we'll do an algebraic perspective. So we've got three graphs here. Okay? Now remember, to determine graphically whether a function is symmetric about the origin, what we're looking for, okay, is if the point xy is on the graph and the point negative x, negative y. So this graph, okay, this would be symmetric about the origin, okay? That means that this is an odd function, okay? If it's symmetric about the origin, it is an odd function. To test for symmetry about the y-axis, okay, we're saying that the point xy and the point negative xy are on the graph. Okay? We can just fold the graph across the y-axis. So this would be an example of an even function because it is symmetric across the y-axis. This third example, okay, is actually neither. It is not symmetric across the y-axis or through the origin. Okay? So in this case, we would just say neither. All right? So let's determine this algebraically now. Okay? This first one, f of x equals x squared minus 9. What I want to do is plug negative x into my function. So when I do that, I'm going to have negative x squared minus 9, like that. Now, negative x squared, okay, means negative x times negative x. That would be positive x squared, and then the minus 9 stays the same. So, oops, f of negative x then is exactly the same as what we started with. F of negative x equals f of positive x. If we get that, that means that my function is even. Okay? If I get exactly what I started with when I plug in negative x, that function is even. That means this graph would be symmetric across the y-axis. Okay? So in my second example, I have g of x equals negative x cubed. So let's plug in negative x. So I'm going to have the opposite of negative x cubed. Now, since I'm raising this to an odd power, my sign is going to stay the same. Right? Negative x times negative x times negative x would still be negative x cubed. Okay, so I actually have a double negative now. Remember, we cannot distribute this negative inside the parentheses. Exponents need to come first. So I need to raise this to the third power first, and then multiply this negative sign in. So the double negative then becomes a positive x cubed. Right? In this case, I get the exact opposite of what I started with. I started with negative x cubed. I end with positive x cubed. That means that this is an odd function. Okay? Now, if we had multiple terms in my original function, I would have to have the opposite sign on every single term. Okay, so let's say we had plus x or something like that here. Okay, then I would need to have minus x when I plug in negative x. In order for my function to be odd, I need to have the opposite sign on every single term from what I started with. Okay, so that's it for this video. The final question is going to pop up asking you what questions you still have.